Let's get this show on the road here. Before we get too far in, I just want to kind of talk about the schedule for the week. So today we're going to do 8.2 and in-class examples from 8.2. And we're going to finish with a good chunk of time early. I'm going to talk a little bit about some IA stuff and show you guys how to do some nice formatting stuff in Word today. We'll do that again another day also, but on Wednesday we're going to do the Chapter 8 activity, and then we're going to do our calculations for our IA. So if you have a data source that you collected, you want to make sure you have that all ready to go. If you're using a survey, we seemed like checked in this morning with some of the first hour people. Seemed like you have about 70 responses or so, which is probably adequate. So we'll get a head start on that stuff on Wednesday. I'll walk you guys through how to do the Excel calculations and stuff. And then on Friday, we'll do the Chapter 8 quiz. And after the quiz, we'll do some more on how to use formatting in Word to get everything in there pretty. And I'll explain to you a little bit today as to why I'm encouraging you to do it the way that we're doing it. Everybody cool with the plan? Okay. So today we're going to continue down our probability rabbit hole here. So we'll start with just some basic rules about probability. So the first is the probability is a number between 0 and 1, or as a percentage between 0 and 100, or a fraction greater than 0 and less than 1. Will Mr. Kulik be picky and mark your problem wrong with no partial credit if you tell me a probability is greater than 1 or less than 0? Yes, that's an insane answer. Insane answers get no partial credit. Just to be warning, Everybody's okay? If I take all outcomes and I add them together, the probabilities must add up to exactly 1. Okay. To calculate a probability, if I know all the outcomes in the sample space are equally likely, then the probability is just the number of outcomes corresponding to that event divided by all the outcomes in the sample space. And the last piece is that the probability that an event does not occur is 1 minus the probability that the event does occur. That's the complement rule, which we mentioned last time, right? I think that you guys suggested as an answer to something quite naturally when I asked you how you did it. Okay. Alternatively, I might express all these same ideas symbolically. So this slide is the exact same information as the previous slide, but here we've written it in mathematics as opposed to English. You should be comfortable reading it either way, but they are saying the exact same things. Just one of them is doing it symbolically and the other is just doing it in words. Everybody's okay here? So if you want, so that when we talk about probability, typically there's 2 different types of probability we'll talk about. There's the theoretical version. This is the probability of the idealized situation and the results that should occur based upon our given information. So if we talk about hey, if I flip a coin, like 3 times, what's the probability of getting, all heads 3 times in a row? You'd say 1 in 8, right? Now, is that guaranteed if I flip a coin 3 times in a row, if I do that process 8 times, am I guaranteed to get 1 time it come out to be all heads? No, there's no guarantees here. It's just the idealized situation. Now, in doing that, we're assuming that the coin is fair, right? That the probability of getting heads is exactly the same as probability of getting tails. In the real world, are we sure of this? What if it's really like 50.1 to 49.9? Are you going to be able to tell the difference in the short run? No, but does that matter? Yeah. Again, this is the theoretical is the idealized situation. Now, most of the calculation and the problems we're going to be doing are going to be using theoretical probabilities. But what if you wanted to check to see if, like, okay, Mr. Kulik said this coin is fair. Like, how would I check that? Well, you'd do like an experiment. You'd calculate an experimental probability. So you'd basically take your coin in question and do some kind of test with it. Maybe you flip the coin 1,000 times and count how many heads you get. Or 10,000 times or 100,000 times. What should you expect as the experimental, or as the number of trials approaches infinity? Is you'd expect the experimental probability to match the theoretical probability, right? If you do infinitely many trials, those should like converge together to be the same. Another example of experimental probability would be like a baseball player's batting average, right? Like you don't know what their true batting average is. You just know what's happened so far this season, right? So your number of successful trials in a batting average situation would be like hits, and the total number of trials would be at bats. Everybody's okay there? So let's look at a situation. It says a baseball player has a batting average of 250, meaning that he has safely hit a ball and reached base 1 out of every 4 times he steps to the plate. In a particular game, he has gone to the plate 3 times and not reached base. Your friend argues that the baseball player will absolutely safely hit the ball and reach base at his next at bat. Give 2 reasons why your friend is wrong. Nate, you got one? Right. So that's like the myth of short-run regularity, where we expect the what's true in the long term to also be true in the short term, which we know isn't really the fact or isn't the case. Everybody's okay there? So that's the one, that's the obvious one, the first one everybody says. What's the second argument we might give our friend as to why they're wrong? This one's a little bit more subtle. The second reason is that our friend is confusing experimental and theoretical probabilities. The batting average is an experimental probability, and he's using it to make a future projection, which is what you'd use a theoretical probability to do. Do you see how your friend is using an experimental probability inappropriately? Because he's talking about projecting into the future using an experimental. You don't do that. Everybody's okay? Next thing we want to talk about are mutually exclusive events. So we say that two events, let's call them A and B, are mutually exclusive, or sometimes we'll use the word disjoint. That means the same thing as mutually exclusive. If they have no outcomes in common, and as a result, they can never occur together. That is, the probability of event A and event B occurring is 0. So for example, if we're flipping a coin, the probability of getting heads and tails on one flip is 0 because they can't happen at the same time. Those are mutually exclusive events, right? If you talk about drawing cards out of a deck, if I say the probability of drawing a face card and a card with the numeric value of 7, the probability of that happening is 0 because there are no face cards that have value 7, right? They're value 10. Does everybody kind of see the idea here? Okay. Now, certainly there can be overlapping events that can occur at the same time. If we look at our card drawing, if I say the probability of drawing hearts and a face card, that is not mutually exclusive, right? Because there's a Jack of Hearts, a Queen of Hearts, and a King of Hearts. There are 3 cards that are both hearts and face cards. Does everybody feel okay with what we mean by mutually exclusive? Okay. So if we have 2 events that are mutually exclusive, we can calculate the union of those 2 events by just calculating the probability of A plus the probability of B. This is true only if the events A and B are mutually exclusive, where they have no outcomes in common. So probability of 7 for face card, that's mutually exclusive. Probability 7 plus probability of face card. Probability of heart or face card, it's not equal to the probability of hearts plus the probability of face cards. You'd have to do that a different way. We'll talk about that. Does everybody feel okay? So this formula is specific to A and B being mutually exclusive events. The biggest mistake students make is using this formula without mutual exclusivity. Everybody's okay? Let's look at an example. So when people create codes for their cell phones, the first digits follow the probability model shown in the table below. So basically like 0.9% of people's first digit on their cell phone passcode is 0. 0.3 or 30% of the time it's a 1, 17.4% of the time it's a 2, etc., etc. Is everybody okay with how we're reading this? Find the probability of the event. A is the first digit is 1. What's P of A going to be? Just 0.3 or 30%. Either is an appropriate way of representing that, or even 3 out of 10 if you wanted to. So it's just the value from the table. Everybody's okay there? Okay. The probability that the first digit is more than 5. What are the outcomes in that event? 6, 7, 8, and 9. Now, that means we're calculating the probability of 6, or the probability of 7, or the probability of 8. I'm sorry, the probability of 6 or 7 or 8 or 9, right? Now, are these events mutually exclusive? Yes. Why? Because your first digit can't be 6 and 7. It can only be one or the other, right? That holds for all first digits for a passcode. Everybody agree? Okay. They're all mutually disjoint, so we can just do the probability of 6 plus the probability of 7 plus the probability of 8 plus the probability of 9. So if we just read those from the table, we get 0.221. Is everybody okay here? What are we seeing so far concerning the calculations? The actual arithmetic you're doing is really simple, right? We're just talking about, like, we're just going to be adding, subtracting, multiplying, and dividing here. You're not going to do anything fancy. What do we have to be careful about? Understanding the question and the words that they're using and what formulas we can use when, right? This is a reading comprehension chapter and making sure we understand what's happening so we know which formulas to use when. Does that feel okay? Let's continue on. Let's calculate the probability the first digit is odd. What are the outcomes in that event? 1, 3, 5, 7, and 9, right? Are they mutually exclusive? Yes. So to calculate the probability the first digit is odd, I can just do the same thing and just add up the probabilities for 1, 3, 5, 7, and 9. I just read those from the table, and I get 0.603. Still feel good? No big deal. How about if I ask for the probability that the first digit is a 1 or greater than 5? Remember, this was event A and B from before. Are these two events mutually exclusive? Yes, right? Event A has just 1. Event B is 6, 7, 8, and 9. None of those are the same. This is mutually exclusive. So we can just take the probability of A plus the probability of B and write it as 0.51. Does that feel okay? What if I ask for the probability that the first digit is not 1? Right, so we'll use the complement rule. So we're looking for P of not A. So that should be 1 minus P of A. So 0.7. Alternatively, still correct, you could just add up all those probabilities for probability of 0 plus probability of 2 plus probability of 3, yada, 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 all the way to probability of 9. Still correct. A little bit more time consuming, a little bit more tedious, but not wrong to do it that way. Absolutely will work. So far, so good. Okay. Find the probability the first digit is an odd number or larger than 5. Are these mutually exclusive? No. Why not? 7 and 9 are contained in both, are outcomes in both event B and C. Correct. Thank you, Grace. So how do we do this then? We can't just add up the probability of B and C, right? We're going to have to do it by hand. So which outcomes are in this set? Odd or larger than 5? 1, 3, 5, 6, 7, 8, and 9. So we need all the things from B, all the things from C. There you can see that 7 and 9 are the two that are making this not mutually exclusive, that these events are overlapping. There are outcomes in common between both of them. So I just copy my numbers in from the table, add them all up, and there we go. What's the, yes?
You can still add all them up together, even if those, like the other two numbers that overlap.
Well, what we couldn't do is add B and C together, right? If I added the probability of B plus the probability of C, I get, what, 824?
Oh.
Which is not 721. So we can still do it, but we can't use our previous work. We'd have to do it fresh. Does that make sense?
Yeah.
Now, what if I did want to try to use my previous work? Obviously, 824 is the wrong number. Why is it going to be the wrong number? What if we counted twice?
Oh, it'd just be like 3.
It'd be the probability of 7 and the probability of 9. We've counted twice. You guys see that? So if I want to get the right number using probability of B and C, what do I have to take away? I would need to subtract the probability of 7 and the probability of 9. So that instead of counting them twice, it now makes them counted once. Everybody's okay there? And you'll get the same thing. Can I said this question. I don't care about this question. We addressed that already a moment ago. What is probability of 7 plus the probability of 9 really, in set speak? What is that event? What? Intersection of what? It's the intersection of events B and C. In general, that is our formula for the probability of a union. The probability of the union of B and C is the probability of B plus the probability of C minus the intersection of the probability of B and C. And that'll work whether the events are overlapping or if they're disjoint. Because if they're disjoint, what is the probability of B and C? 0. Right? If they're disjoint, what's in the overlap? Nothing. So that formula is like the more general version of what we just looked at because it works whether the events are disjoint or not. What do you guys think? Is okay? No big deal, not a very complicated idea. Guess what? That's it. Oh boy. Good, great googly moogly. What is my recorder trying to do right now? What? I'm so confused. What is it thinking it's doing? I don't want to do any of these things. Okay. Well, this is just going to get... I am bewildered at what it thinks it's doing right now. Okay. Okay. I don't know what's going on, guys. This is acting really strangely. Why is it it thinks it's done there, but it thinks it's still going. I am so confused about what this is doing. All right. All right, this is just going to be split into two pieces, I guess, for today. Recorder